5, 4, main engine start, 2, 1, 0, and liftoff of the Delta II rocket with Phoenix. Distant science outpost seizing clues of the evolution of the polar region of Mars.
Both verniers and the main engine chamber pressures looking good.
We couldn't simply just make a sensor with all Earth components. When you send a sensor to Mars, it's got to go on this lander, which by its nature has to be super light. And essentially we were given a parameter of, you have to build this to 100 grams, nothing more. When you do that for Mars, you've got to economize on weight, you've got to economize on power, you've got to produce the kind of instrument that is carefully honed for this application, which means it has to be robust, it has to be accurate, it has to be consistent, it has to be the whole package to be able to go on this lander.
Just the amount of work that it takes, to pour into one single instrument, the amount of validation, the amount of calibration, it's just extreme compared to what we do. So our production processes here, I feel like, are pretty extreme. I mean, we test every single function of every single instrument, make sure everything that we do is within specification here, right? I mean, that's just the way that you have to do when you manufacture sensors. But this was, 100 times that. You have to test it under this huge parameter space of, of temperatures and pressures, and just really meticulously go through this entire parameter space and make sure everything's right. And that's just a whole different mindset than working on Earth.
We were going up to icy northern Mars so that we could go somewhere where water actually was. We could literally follow the water, not just try to find evidence of water billions of years ago. The thermal and electrical conductivity probe was probably the only instrument on Phoenix that worked perfectly from beginning to end.
It needed to integrate with all that was on the lander, so it has to talk to everything, it has to be able to communicate back and forth, and most importantly, it has to make sure that it doesn't pull down the rest of the mission. It can't fail electronically, it can't fail when you're inserting into the regolith, it can't get stuck there and not be able to be pulled out, because that scoop is actually pulling in the Martian regolith and delivering it to things like the optical microscope. And if it doesn't do that, the mission essentially fails. So having a robust instrument, having an instrument that's going to get it right every time, and it's going to perform flawlessly, was not just an expectation, it was an absolute must.
Really, the primary reason that thermal and electrical conductivity probe went to Mars was looking for unfrozen water, looking for liquid water, which of course is necessary for life as we know it. And there's a direct translation between that search for water on Mars and the things that we're doing here presently. I think that METER is incredibly well equipped to help the world by helping to alleviate the water shortages that are coming. So especially in the agricultural space, there's a lot of wasted irrigation water, and we have a really great tool set in terms of soil moisture sensors, plant sensors, atmospheric sensors, plus the telemetry to turn it into actionable data with a piece of software. And I think we can play a key role in this struggle that's coming up to try and make sure that the human population is fed. And that's really where I feel like our impact is going to be.
Being able to put something that we did at Decagon, at METER, onto this lander and go make measurements on Mars, it was extremely captivating. As we talked about the potential of this to go make these critical measurements, like, hey, you could be the first one to discover water on Mars, to identify that with an instrument. And being that water is such a key measurement for METER, it's really what we're interested in doing in the soil plant atmosphere.